So let me get started. Going to be talking about building streams out of hot air. I'll get to the implicit joke here in a second. Coinductive types in C++ senders, and I'll explain that too as we go along. I'm Steve Downey, a software engineer at Bloomberg. Been at Bloomberg since 2003, so a little bit more than 20 years. Work currently in the C++ infrastructure group, where we own all the compilers, the build flags, and a lot of our general C++ practice, how we should do things and make recommendations in cooperation, competition with some of the other low-level C++ groups. I'm also been involved for the last 6 or 7 years with WG21, primarily in text, because in a prior group I was in, I did our conversion of our backend for our email system from storing in unknown blobs of encoded text all into UTF-8. So I know lots of things that don't work, and we shouldn't standardize. So we're going to be building sender streams out of senders when we eventually get there. Senders as in sender receivers. So we're going to build an async stream, an infinite list out of nothing but senders. Along the way, we're going to take a look at something like the last 80 years of computer science, including some areas of pretty current research. Having a better idea of how senders and functions like them are grounded in theory gives us a better idea of how they can be used and what they're supposed to do, and where we can borrow designs and insights. Because we don't just borrow syntax. On occasion, C++ has pursued other languages down alleyways to beat them unconscious and rifle their pockets for new semantics. This was originally a quote about the English language by James D. Nichol. I asked him if I could amend the quote, and he said, "That sounds awesome." So, okay, this was a quote from Gerald J. Sussman, the lecture Computational Objects, which is available online. Link is in the notes in that. This was part of the lecture series for structure of interpretation in computer programs. But what he said is, I'm going to show you an even more horrible thing, a definition of cons in terms of nothing but air, hot air. And what he was talking about is that we can use just lambda expressions. He was working in a Lisp variant scheme to build data structures that act just like we expect data structures to act, but there's nothing really there. P2300 senders, they're, as we've had in a few lectures, they're computations that are going to be performed. It's an object that describes work that you'll ask for work to be done eventually. So when we're trying to figure out how to plan what we want in a sender and how to use them, taking designs that suspend computation already is a good place to look for. And models that do so in an otherwise strict evaluation environment can be easier for reasoning about for C++. C++ is by default a strict eager evaluation language. So you want to think about, if I was in a strict eager language, how do they express laziness? And the key thing is almost always you hide it behind a function call somehow. It's like, well, what else do we have to do? So So we can implement a lot of this stuff really directly with C++ lambdas. It gets gotten even easier now with deducing this, so we can cheat on like recursive stuff, and we don't have to figure out how to implement like a Y combinator or a fixed point operator. We can say that is legal to do. I can just pass this parameter into my lambda as a deduced this self reference, and it's good. Theoretically, yep, we're good. Practically, we're good. Okay, quick overview, Lambda expressions. Lambda expressions came from Alonzo Church. It's a symbol manipulation game. It's as the rules lay out, there's nothing about computation in them. This is all a game of what can we do about substitution and evaluation of these things so that we can then maybe talk about computation, but computation's hard. This is simple. So it's like we've got x, a variable. Lambda x dot m, it's a function of one variable with some definition m that will substitute in the x into the definition wherever it was, wherever it's passed in, and it's all just symbolic. There's no meaning associated with it. And mn is an application of the function n to the argument n. And you just do the textual replacement, and this is pretty much all there is to lambda calculus. This is great for doing math because the simpler things are, the less likely you are fooling yourself or hiding something in some definition somewhere. This is so simple, there's nothing hidden, but it turns out to be ridiculously powerful. The core other thing is beta reduction. It's like if you apply a lambda term to its argument, you're just doing the replacement. It's all textual. The fact that it's textual does lead to some problems because in the untyped lambda calculus, you can say nonsense, and that's legal. It's, there's no meaning associated. Type theory largely grew out of how do we make these things make sense internally such that I could reject things that don't make sense before doing these kinds of calculations. Little bit of notational sugar. The core lambda calculus doesn't have multiple variables, multiple variable arguments. Everything is just, it's like single arguments that return single argument functions that return single argument functions. You can translate them back and forth, and it's easier to talk about with this rule in place. So you don't have to have cascades of lambdas. Same problem as in Lisp, where you get cascades of parentheses. You start to be able to ignore them, but it's easier to talk about this. The other thing that it's like currying sugar, that it's like, so if we've got a function f that takes x, y, and z, that's what it means. We evaluate from left to right, going out with that. Be using this a little bit. The other important thing I'm going to be talking about a lot, closures. It's a function that retains access to the names in the scope it was created. So we can capture those things. In C++, we've got ways of describing how those things are captured, but that's really the core technique of what I'm going to be doing here and the way we cheat in terms of, well, how do I, if I want to have like a pair of int, where are those ints coming from? We hide them in a closure. And higher order functions that return functions. So we take some stuff in, we do some of the calculation or defer things and return like a lambda object that's like, here's how to do the rest of the calculation when you give me the rest of the things that I need. Another important thing in terms of what I'm talking about here, things are what they do. What I mean is, it's like, if I can figure out a way of taking this ridiculous collection of lambdas that I'm saying represent a pair, can I describe how to use those the same way I would std pair? And if the function that I am doing this in acts the same way, this lambda nonsense must be a pair in some way. But even if there's no class pair or type pair, it's like it performs what we want, so we can in some say it is what we want. And there's some techniques I've used to help convince myself I'm not lying to myself, because this is really easy to do when it's like, you are the easiest person for you to fool. It's like, you want to think you're right, so if you don't test things, you will say, oh, of course, that's right, that's right. Here's an example of a technique I've been using. I was talking about this last year. Gaspar gave me, I can never get his name right. Gaspar gave me some hints to make this better. I've improved it since then. But essentially, what we want to do is, if I'm talking about something that might be an either, I want to say these are the things I can do with the either. I want to be able to say, give me an either that's holding the left, one that's holding the right, check if this is a left engaged either or right engaged either, from left or from right. Either is a function that says, here's what you do with the left. If it's a left one, here's what you do with the right one. Give me the result of each, whichever of those functions apply. So if I write a function in terms of this, it's like, whatever I'm instantiating this over acts like an either thing. This is a bunch of code, but this is how you would write this and say, I want to use std expected as an either, which is actually a little complicated because either doesn't care about the left and right side. Expected does. Expected has a lot of built-in support to say, the left side, the normal side, is what you should get. The other side is unexpected and an error. They're not equivalent, but you can get rid of that. So, and that's what a bunch of this code does. So I can say, here's the either type class implemented for std expected left and right, and I didn't go in and make this as friendly as it could be, so you have to like repeat some of the parameters in this. But then we can write a test function that's going to take in as a non-type template defaulted template parameter. It's like the either type class that I'm going to instantiate on the other bits that I'm using for this function. And then I'm just a test function that's going to use these various bits from that map. I can then, here's some of the other things that I'm doing, and I've got static asserts that it's like, I'm not lying to myself. This works when I compile it. The case switch, so it's like I want to take my either, and so I've got an either double, and if it's a left, I'll return 2 times. If it's a right, I return 3 times. I can use these with the other things that I've got in the type map, and confirm that I'm getting the answers that I expect out of it. So then when we call the text function, I have to tell it what kind of thing I'm using, that my either is an expected of int and double, and the left and right side are int and double, because generically pulling this stuff out is tricky. So slideware examples. So So I call it this way. The test function and takes the type, the non-type template parameter, instantiates it, gives me a map for the names that I want to use inside the function and how to implement them for an either. And I can do that and have in the test, we won't go into it too deeply, using some of these other ridiculous things I've come up with to say, this is an either, because it works like one, because I can write that type map, that class map. This is also very much how type classes in Haskell are actually implemented. Much nicer sugar, but the compiler just says, oh, you said you required that this thing have the type class of monoid. That means you've got an empty and a map function for it. So I'll replace those with the appropriate definitions that you provide. It works very, very much like, that's why I was doing this first place, the concept maps that we had in C++11 concepts, explaining how your thing models the concept when you don't have quite the right names. We miss this sometimes. We've got a lot of things in the standard library where we give things domain relative names that represent the same kind of thing. So it's like and then and transform, then and transform are really the same thing. It's the functional map. Take whatever inside the thing, apply the function to it. But the name, it's like map, okay, already we've used that name too many places. We could get, this is actually why Haskell calls it fmap, because they already had a map, so they had to give a second best name to things. Calling it fmap on a particular type, no one would remember what that does. You want, when you're working with a known type, a good name that works with that type. When you're writing generic algorithms, that you might want to have a generic algorithm that works with either a sender or an optional or a range, because there are algorithms that you could write that work with all of them that are provably correct. Don't do the same thing at all, but plug together these operations in ways that are it's like known to be correct. And it'd be nice to be able to write those more easily. Yeah.
Do you think you could use concepts to represent type classes? Or like
you can't.
You cannot? Why not?
Because we cut that out of the whole concepts thing. It's like we don't have a way of explaining to the compiler directly with concepts that when I say this name, I mean this operation. There's no way to, we can't write the translation to say, this is in this function, the bind operation is the appropriate thing for these different types because they have different names on those types. I've got some library hacks in this to help us get that back, but it's still kind of messy and not terribly user-friendly.
I was just wondering about like using a title. Like you can't like always say it's this name because that's true, but like if you have like something like a title or some other like, if you want to implement this type, just implement this function, and then the concept will pick it up, and then you can write against the concept. This is the idea. But
yeah, the problem is when you want to go the other way. It's a because I want to write my super generic function in terms of bind and join and fmap. Nothing has those names. We've given some other name for exactly those operations for types in the standard library. So we want the reverse mapping. C++11 concepts had a way to express that, but we lost it. If you want to make Dave Abraham sad, go ask him to tell the story again. I got him to do it last night for a few people.
You considered like cross-bind concept.
So Yeah, here's how you might do it with it. I've got a pair type class. It's like we do the same thing. We want to have pair first, second, and apply operation for that. It's like once I have this, I can write generic algorithms. I just have to write the mapping between them. And yes, concepts are really useful here because I can assert on the concept that your implementation, your claimed implementation does the right thing. So, or has the right approximate shape at least. It's like, you can lie, but, so it's like we could write the pair type class for pair and then write functions or test functions in terms of this type class, and like whatever we're supplying for the test functions we can use. Yes?
Is there a reason they're not marked static?
Sorry?
Is there a reason they're not marked static?
Oh yeah, well, in this case, some of these might be objects rather than, it's like, this is an instance of something in the most general case. They might be static. It's like, they are const expr in this case. It's like, in pretty much all the cases that I've been doing with it, this is so transparent to the compiler, it ignores it. And it's like, it just swaps everything in. Static might help. I'll try it out. So it's like going through the rest of the test function, how to test apply. We call the test function, explaining what our types are, and it does all the deduction, and I can run the same test function on a lot of different pair-like things. So let's switch over a little bit. Implementing data with Lambda, unnamed functions. It's like, this is our hot air. It all comes down to closures and partial applications. Closures are where we're stashing the data until we need to use it. Partial applications is, I'm going to return you a function that you're going to give me functions that let me get back at the data I'm holding on to. So it's like partial applications means we get to defer using the values. And if that sounds a little bit like what we do with senders, yes, that's or it's like, or task or other things. We're deferring what we want to do until later. This is also very related to continuation passing style, because we're going to be taking a function that's what we want to do with the value that we're holding on. The pair doesn't know what to do. The pair knows how to call the function that you give it. It's like, and there are two main strategies for encoding this stuff, Church encoding and Scott encoding, which are very closely related. On recursive type, Church uses a fold technique. Scott encoding is pattern matching and visitors, which are very tightly related. I'm trying to get a hold of one of the people in doing some of the original Gang of Four design pattern works. I'm pretty sure he borrowed the visitor pattern out of his implementation work in language development. It's like, there's a lot of current excitement that these things are similar. I'm like, wait, no, you're getting it backwards. We took visitor from how we implement pattern matching, not the other way around. But the syntax is so much nicer. That's why pattern matching is nice for users. Visitors are a tedious annoyance. Yeah, it's for recursive and non-recursive types. Scott and Church, Dana Scott and Alonzo Church, they work exactly the same ways. So the encodings are the same for like either pair, maybe Booleans. List is a recursive type because list works on lists. Like you construct a list out of a value and a list. You get the tail of a list that returns a list. So the type shows up on both sides of the arrows. Recursion makes everything more complicated. We know we can do recursion, but it's like It's very easy in C++ to fall into types that you've managed to make recursive, and then the compiler tries to find the end and doesn't, and will eventually run out of memory or give up. Exceeded template instantiation depth or whatever. It's like, so all of these techniques end up involving some way of breaking that, so that this type is logically recursive, but you hide it enough from the compiler so the compiler can defer figuring that out until it needs it later. So let's look at either without much any real C++ code. I'm using Haskell for this just because but you really don't need to know any Haskell. This is the obvious definition. It's like an either A, B, you construct a left with left A, a right out of right B. It's like, because Haskell is originally written by programming language theorists to write their own paper, they wanted the syntax as terse as possible so they could keep their page counts down. Translating this stuff into C++, it's like top stuff is Lambda calculus. It's like in the encoding we're using, bottom C++. So I'm going to say when I want to construct a left either, I'm going to take the value, I'm going to capture it, I'm going to take a function. It's like, I'm not describing what I'm taking, but that L is a function that I'm going to pass the captured value to. So it's like, you tell me where to send, where to deliver the value I'm holding. So what I'm going to return is a higher order function that captures what you gave me to do, the value that I'm holding. It's like, takes a single parameter that does nothing and returns the left of A. Right does essentially the same thing. It's like only takes right of supplies right of B to it. It's like, for doing case analysis, we're going to end up passing two functions. Or actually, this is sugared. It's like, so I'm capturing one, passing something that'll capture the other. That's why there's two parentheses. It's like, this is higher order. The either is going to take one function, return a higher order function, take the other one, and return something that, when you evaluate it, picks either the left or right function, the continuation that you want to use, passes it to the pair knows how to deconstruct itself and send its parts back to the other functions. It's like,
are we just using single argument functions here on principle?
On principle
Okay.
At this point. I'm going to stop doing that shortly. Because it's tedious and annoying and no one really wants to do it all the time. This is like, yes, see, I can do it. I can do the direct translation, but we don't really want to. We can do the similar things for pair. Pair is even easier. We have a constructor that takes two values and says, here's how you get a pair of the other of a left and a right. So yeah, I'm skipping the single functions that return functions. It's like, we construct a pair from two values. I capture both of them. This function will take something the function that's being returned will take something pair-like, hopefully constructed with this, but anything that's got the right shape will do, and will call what you give it with the two values it's holding on to. What it's doing in here is the core of pattern matching. It's like, or visitor. This is the visitor pattern. This bit in here is saying, you told me a left and a right function to call. I know how to deconstruct that. I'll call what you tell me to do for you. No actions are happening here yet. This is just setting it up for use later. So how do we use it? Build these things up. The two key operations on a pair are getting the first and second out of it. To get the first out of our pair-like thing, we're going to have a function, captures nothing, takes what to do on the left, what to do on the right, and just returns left. Or it's like, well, no, sorry. This isn't what to do. This is going to be called by pair, which is going to deliver its left and right value to the function that you're handing it. And since we want the first one, it's like, you gave me the left or right, I'm first, I'll give you left. Second works the same way, only gives you back right. So there's a lot of deferring of these, but the core thing is the functions that are getting called work the same way as the constructor does. And this is the general pattern for how to do these encodings. These encodings are also entirely mechanical. Like you can run a computer program, and this is the way a lot of languages actually do this. It's like it says, oh, given this definition, here's how to encode it just using functions. So like, you teach the computer to do that. You can have some meta machinery that does this. We could, once I get a little more time and a compiler that really does reflection, you could do this at compile time with reflection and some and splicing. Give me this definition. I'll give you these functions that are C++. And callable by C++, but work just from these descriptions. Context for parsing isn't that hard either. Now, thank you, Hannah. We can do the similar thing with maybe. Maybe being like, there is a value or might not be a value. There's a nothing side that doesn't hold anything. There's a just side. One of the interesting things with using the church encodings, you wouldn't think that you've got some sort of tag discriminated union for implementing this. You don't in a lot of functional languages. It's just, I construct functions that remember, it's like, which way I was constructed so I know how to deliver the values that I'm holding. In the nothing case, there's no value. In the just case, there's just the A. And send it to whatever you tell me to use to continue on with the work. So here's an implementation of nothing and just using C++ lambdas. And it's like, just as I had before, we return a function. It's like, since has no data to pass it, all it's going to do is call the function that you gave it. Just is going to do nothing but call the function with the value it was holding on to. So it dispatches, it remembers how it was constructed and dispatches with a visitor with the data it's holding on to with whatever functions you're asking it to do. So we can write the rest of the normal interface for a maybe, is nothing, is just, give me the data out of the just side. The abort is deliberate. So I've got to pass in what for a unknown maybe type what to do if it's a nothing. If you asked for the just side and you gave me a nothing, you're wrong by construction. You should have checked first. So terminate, abort, all bets off. It's like, there are better APIs. It's like, in a safer API, you might have a default value here to hand back instead of just saying, you tried to deconstruct the just, it's like, and this is really a nothing. But here again, we have to give to our maybe like thing the what to do for one case, what to do for the other, and it takes the data that it's already captured and passes it forward to the continuations that that you want to use. This also ends up giving a lot of nice features to the language at all. So yeah, here's the case analysis. It's like a maybe is a function which takes a default value and gives me either the default value if it's a nothing or the just value if it was a just. So it does the captures, holds on to things, and passes things forward. This is the safer API that you want to use if you're not sure what kind of thing you're working with. List is a really interesting case, though. Now it's like, because we construct lists out of either a base empty list, or we construct, which is where the cons originally comes from in cons cells. These were constructions. So we construct it out of a value and a list we're sticking it in front of. There are two ways of translating this, one of which is efficient and the other which is simple and easier to get correct. And types. The efficient one doesn't type very easily. Fortunately, we don't have to worry about this because after the mathematicians proved you can do it, we say, we can cheat now. It's like, I know recursion works. I don't have to prove that it works. It's like, I can, for example, use deducing this to say I can call myself now and it's all fine. I don't have to worry about getting the name of the thing that I am to be able to call myself or whatever. Constructor for nil, we take the what to do in the nil case, what to do in the cons case. These are functions that we'll call. And for nil, we just return the nil side. So we're going to call, this is the visitor for all list operations have to know what to do for the nil case, what to do for cons case. Nil constructor remembers I'm nil. I'm just going to call the nil case. The cons constructor, more complicated. It's like, this ends up building a fold where it's like, you take the X and list of X's that are coming in and as free parameters, you pass in what to do in the nil case and the cons case. You then cons together those, the X, and as a parameter that's going to get passed to cons, the list of X's, your other list, and the nil and cons that you're about to take, that you're returning, because you're returning a higher order function. There's a reason we think Alonzo Church was a genius. Not at all simple to have invented. Now it's just merely complicated to figure out, like, what do I know, when do I know it, and what am I going to do now versus later. Scott encoding is a little bit simpler. We ignore the fact that we're recursive, and this is a problem for typing, but in C++, we can ignore it a little bit. So I'm going to end up calling the function that you gave me as the continuation for the cons case in constructing this list. And it's like it just works because we've already got recursion in the language. A function can call itself by name. And now with deducing list, a lambda can call itself if you gave itself a deducing this self parameter. It's like deducing this has opened up all sorts of terrible things we can do to ourselves and our users. It's like we can write the observers. There's the church encoding. I looked it up. You are not expected to understand that. No one does. It took Alonzo Church and a few of his compatriots like a couple of years to get this worked out. And if you've ever seen the equivalent thing for doing predecessor on the piano numbers where you just have 0 and successor, it's a nightmare of how does this work. It does, provably, but it's Scott's a little easier. You just call yourself with what's been passed in, and you take for granted that recursion is allowed. At the type system level, recursion's a problem. Fortunately, C++ already has the sugar that it's like, you don't have to tell me how to do recursion. I know how to do recursion. So here's C++ code for a Scott list. So we mechanically translate that prior bunch of code into this stuff. We've got the std abort again, where if you ask for the tail of a nil, you've asked for something meaningless. In practice, there's different answers for it's like how to use this safely. Some languages will like return tail of the nil list is nil. It's the empty list itself. That can be theoretically unsatisfying, but safer. We don't actually need to worry about that too much. And here's the deducing self. So it's like we take this const auto self parameter. So now I can capture self for calling it later in this lambda that I'm returning. This actually works. I've got test cases. It's like they're also amazingly constexpr test cases. This is transparent to the compiler, and it's like you construct up one of these lists at constexpr time, ask for its length. The compiler thinks for a bit and turns that into just a number. Like it's like there's a literal 7 if you've constructed up a seven thing. A lot of work on the compiler's part, but it's very efficient. The transparency of this, along with senders and receivers, gives the compiler a lot of latitude to make some of this stuff that's complicated and looks like there's a lot of overhead into something that works pretty transparently and efficiently. Okay, so what are the patterns? I was saying we can do this all mechanically. So it's like for non-recursive types, if we've got some type T with constructors A, B, and C, and just to be clear, I don't mean C++ constructors. In programming language theory, constructors usually have individual names, not the name of the type, because it's easier to talk about things with names than saying, yeah, there's an overload set for the constructors, and you have to figure out which one I meant. We can translate this into C++ that way, but we don't necessarily have to. We can have functions that are factory functions instead of being constructors. So we've got, it's like some data type T that's generic over 4 parameters. There are 3 constructors, which each use a different mix of the various types, various parameters that they're being passed. This gets messy to talk about because there's going to be a lot of indices and it's like a lot of repeated stuff. It's like, so we want to first convert those constructors to functions. So, and you can sort of see the pattern here. So every constructor is going to take a function that handles each of the cases of the constructors. They correspond exactly to what those constructors are, and it's going to select out from the list of the visitor that you give it the right one to call and the parameters it already knows about. So it captures whatever it's taking. So it's like when we're translating the A constructor, we capture its 2 parameters. We say we're going to take a list of functions to apply that could apply to anything. This is our uniform interface for the type. And then we call the right one because we know which one we should call because we're making one of these thing, and pass in the variables that we held on to. So now we've got these translations for each of these factory functions. So now when we say I want a function that takes a t, logically we're going to define it by pattern matching. We're going to say, what do we do for each of the cases for a t? And ignoring what the body of those functions are, you need to know what you want to do with them. You're doing whatever. At the mechanical level, we don't know, nor do we care. But I know that it's like, if you're giving me an A, it must have had 2 parameters, and I know their types. If you're giving me a B, it had 2 parameters. I know their types and what they were. If you're giving me a C, for the case we're talking about, you're only giving me 1 parameter. This all matches. So inside the body, you can work with X, Y, or Y, Z, or W, and everything just works fine. But as we know, visitors are really tedious to work with. We'd like to be able to, and it's like, I really hope for 29 we get pattern matching so we can just write this in a more straightforward way rather than having to write out the visitors by hand. So when we're encoding one of those functions, it's like, it's going to take an object of our t, it's going to pass each of those cases to the object, and it's going to use the visitor pattern to pick which one of those to call and make the call for you. So t is the result of one of those factory functions. It's like, and it's like ends up calling it. And this is actually how complete pattern matching is implemented in real languages. It is syntactic sugar, but it's nice sugar, so you don't have to do all this stuff by hand. So a type T is encoded as a function that takes functions for each of its constructors and does the right things with those and forwards to it. That's the continuation and continuation passing style. This is how pattern matching works. There's a lot of overlap between all of this. I actually got down this rabbit hole because I want pattern matching, found out that it's like, well, I started to get interested when we might get pattern matching in C++23, and then it's like we didn't. Then it was like, well, we're pretty sure we'll get it in 26, but I wanted to start writing code today. We didn't. We're going to end up with, it's like, my bet now is kind of like bind and lambda that both showed up in C++11, where bind does what you want to do with lambdas, but couldn't, because one's a library solution and one's a language solution. I'm thankful for that because I got a working bind years before I got a compiler that could do lambdas. I think we're going to end up with a similar situation with C++26. We're going to have I hope to have a nicer library solution for visitors. Yeah.
The library solution is called std overload.
Yeah.
It's just terrible solution.
It's like, and I know just enough about it to know that the the implementations everyone uses have enough edge cases and problems that we really want a language version of it that knows how to do all the forwarding and such that you can't quite write yourself without a lot of really ugly macros. But now that compiler writers are writing in modern C++, they share our pain instead of asking, why do you need that? You've got all the tools you need. It's like, it still takes longer to get a language feature rolled out. Bar much higher. We can never take back a language feature. We can say this library feature is broken, don't use it, or has like caveats or whatever. It's like broken library features are really annoying, a bad thing to have. Broken language features are cry forever. Okay, so it's like we can do, for recursive types, this is all the mechanisms you do it. This is mostly here, so yes, there's a mechanical way of doing all this. Zach?
I just want to let you know that there's in my estimation, there's like a 99.9% chance we're going to get Michael Clark's pattern matching in 29. It's in 29.
29. Oh yeah, it's like
it was ready to go.
We can't.
We just didn't have time to do the work.
We came within hours.
Exactly.
It's like I know. It's like I am so salty. It's like I feel kind of like it's like I was in the wrong room. If I was there, maybe we could have. It's like, but I was doing something else important too, and it's just like, and it's again. Language features have to be, everyone has to be convinced it's right, or there's some, because all it takes is one person pointing out the flaw to say the whole thing is flawed, even if everyone else is like, no, it looks fine to me. Scott encoding is actually a lot simpler, but for all of this, this is mechanical, which is important because it's like, if you're going to embed this in your language somehow, or even doing it by hand, you want just a procedure to be able to do these. Now, there's a lot of connections with this stuff to other parts of programming language theory. Church and Scott encoding of product types is just folder, the generic fold operation. Catamorphism is the fancy word for extending fold to some types instead of just product types, because you have to be able to deal with both cases now and explain what to do in each of the cases. But that is like how the encoding works. Visitor, gang of four visitors is an implementation of pattern matching. It's like, and it's all the same technique. And this is also related to continuation passing style, because those functions that you pass in are what to do next. Continuation passing styles also guaranteed tail recursive, a lot of nice other features. In particular, for what we're going on right now, senders are continuation passing style. It's like sender doesn't delivers its result to where you tell it to go. That's the continuation passing part. The cool part about senders receivers is you don't have to deal with that machinery yourself. There's a consistent pattern that's built into the sender's DSL of how things hook together. So it's like when something is sending a value and you pipe it into a then, it pulls the value out and calls the function on the other side, and that's all done for you. Another slight diversion, which we'll get to though, data and codata. This is a fairly recent, like post-1990 recent, which does mean it's like likely after some people, before some people were born. But in the practical community that we're in, most of what we do day to day is utterly recognizable to someone who took programming courses in the 80s. It's It's like most of our algorithms in the standard library are almost directly out of the Sedgwick algorithm book I had in like 1987. There is newer, cooler stuff, and we're getting some of these things in. But codata is a way of talking about what if, instead of being concerned with how we make things, if we're concerned with how we unmake them. How do we pull apart the values into useful parts? The co it's like one of these pointing the arrows in the other direction. And it turns out to be a useful way of talking about a whole area of things. It applies, infinite types were one of the first areas that people were like, wanted to be able to talk about. In particular, there's a lot of work with streams where constructing the stream is actually not something that's part of the stream idea. They come out of the ether by some other entire mechanism. But once you've got a stream, it's like you can deconstruct it or stick some other value on the front of the stream or maybe on the back of the stream and do things with them, but not just give me a stream to start with. And this models some very real life things. And a lot of this is new research. Like the papers are from the early 2000s or maybe 2015. The biggest thing, this was a paper a few years ago. Like it's a good summary paper. Like you read this to figure out what these other papers are talking about. But it's like you're switching your focus from how do I make things to how do I observe them. So switching the focus from way values are built, introduced, to the way they're used, that they're eliminated. This also has connections to things like the borrow checking and linear type systems, where you want to make sure all values are used or not used at all, and in particular, not used twice. Codata also turns out to be a great way of describing things with state, behavior, identity. This is one of the more successful theoretical handlings of object-oriented programming. It's in programming research, it's been very unsatisfying having a widely used and effective body of techniques in object orientation without being able to actually describe why it works at all. It's just like, for a long time, I was actually a Smalltalk programmer at one point, professionally paid for it. Before I got even involved in Java, it's like now I'm back to C++. But there's a lot of really effective things. It's like in power and description, being able to model the real world, which is full of objects that have state. It's like not values. It's like, this chair and that chair are different chairs. It's like in a way that like this 5 and that 5 better be the same 5. And 5 should never become 6 by itself. So objects change over time. They do things. They're distinct from other instances, very much unlike values. It's one of the first times I've been here that I think we haven't had one of the value-oriented programming talks. But I'm very much in favor of value-oriented programming because it's way easier to reason about. It's like I don't have to worry about things changing out from underneath me. And I hope the compiler makes it efficient. It's like references turn out to be a good model of codata, not data. You can't just construct a reference by itself. It's like you can't say, give me an instance of a tref. It's like, no, I can't. It's like you have to observe a reference, and that observation may be entirely invalid the instruction cycle after it. Like it can change out from underneath you. So references are more like codata than data. And this in particular is why putting a reference in a struct turns out to be so problematic, because structs are otherwise just product types. But suddenly you put a reference in there and you get none of the rest of the special member functions because we don't know what to do. The compiler can't figure it out for you. You might be able to explain in your particular case, but we can't do it generally. References are in some ways a single thing that describes a whole stream of data. It's like if I pass you a reference and you observe it a bunch of times, you can see this other thing having modified it. You can't guarantee that you get all of them because everyone else could be changing. Hopefully you don't care. But why references are harder to work with. Streams are the archetype codata type I mentioned. It's like the only on a codata style stream, the only thing we have is how to deconstruct it into a value and a rest of the stream. They're always infinite. We don't have an empty case. It's like in a programming language, this means that your deconstruct might block until more data arrives. But this models a lot of real world things. Price of IBM. Like that's a stream of data. It's like I'm going to ignore the possibility that IBM goes out of business, but even then, like you probably can still ask for what its current pricing is, and we tell you something. So we define streams by how we work with them, not how to make them. So we invert the our visitor. So here it's like, so I've got how to read the head of a stream, get a value out, get me the tail of the stream, that gives me another stream that I can then keep using. Notice though, I can't make a stream from this interface. And it's like head and tail are functions here. It's like, as I've written them, that's they're nullary functions. They don't take any arguments, but I can call them. So it's like, this helps in type theory. It's like, so this is an abstract data type. It's not describing how to make streams. It's describing what you need to provide in order to be a stream. It's like, there are language extensions that'll like simplify this declaration and provide all the helper functions that we'd like automatically, making it easier to reason about. So the language can help type check things. Not C++, don't worry about that. But if we're encoding something that's code data, instead of encoding the construction functions, the factory functions that we want to use, and figuring out how to pattern match or visit those, we encode the eliminators, how to observe the things and pattern match or visit on the observer functions. So you tell me for your stream-like thing, how do I get the first element, and how do I get something that if I ask it will give me the rest of this? Then I can continue to program with it. And it turns out we're on firm theoretical basis. So it's like, this isn't like, I know it works, but I don't know why it works. Well, I might not know why it works. I do now, but it's like, there's firm basis for this, so we can proceed in confidence that we're not somehow making some terrible type theory error that's going to cause unsafety and like we don't know what's really going on. So the other thing that is important is like, let's get to the main part of the talk. Well, I've got 20 minutes left, leaving a little time for questions. We want to implement senders. Like, that's what I was talking about saying I wanted to do. So what is a sender? It's a description of async work and send or deliver the result of that work to a receiver. The machinery inside the sender-receiver framework lets you plug senders and senders together by sort of implicitly constructing a receiver that sits between them that connects everything together. That's at least one way of looking at it. Implementations, it's like with more information can do a better job, but it's like they plug together in well understood ways. And when you're working with the sender, you like eventually use something like a sync wait that gets you back out of the sender realm and constructs a value. But most of the time, you're just plugging things together, describing what you're going to do. So it's like senders need completion signatures. We've had a lot of, it's like, depending on which tracks you've been in, it's like you've seen this a few times. They can advertise, they must advertise what they want on their value, error, stop channel. Right now, I'm only concerned with the value channel. We're going to pretend there's never errors and you can't stop these. Like, you could, but just extra noise for what we're doing here. So we want APIs to provide hooks for. It's like you get the completion signatures from something. And the sender handle what? Can the receiver handle what I want to send? Connect, how to plug the things together. You implement these when you're implementing a sender. This is the level below the normal application developer API. It's like it turns out that the API we've given is sufficient for doing any work with senders and receivers. It's not the best way necessarily, but it's like you could do, and I will be doing a lot with just and let value in this, that you can get almost all the way. It's kind of feels kludgy sometimes, and you'd like to write a sender that reifies some of these patterns. So yeah, out of the box, we get lift a value into a sender. We can read the environment, which we've talked about in other talks, deliver that value, and we can schedule, we can start work on it. We can say, this is an empty starting point that gives me a way to go forward with everything else. Whoops. Yeah. Hold on. I hit the wrong button. I hate when this happens. Here we go. So, yeah, it's like talking about sender factories. It's like these are things that produce senders. It's like we've got adapters that take senders and convert and produce things that, when connected, are a sender. I confused myself for a couple of weeks because constructing a then and a function is not a sender. And if you try and use it as a sender, you get the most confusing error messages out of the compiler. But it's like, so it's like, then is the functor interface, let value and such, or the monad interface, on how to switch, when all, join a bunch of them. Then let value, necessary and sufficient. Those two let you do model any control flow construct you might want to. Not necessarily the most straightforward way, but it's like once we have those, we can build more things on top of them. Senders can be user code. They're currently kind of expert friendly. If you saw Robert's talk, it's like 90 minutes of, oh my God, that's a lot of code. It's like, they're not intended to be expert only though. In particular, the task that has good interop with senders and receiver is probably how most people are going to write concrete senders. If I had about 20 minutes more this morning, I'd have an example of that. So I'm going to show you, though, some code examples using just some of the raw tools of either, pair, and stream. Let me pull. Switch to, it's like, I want, nope, wait. Off the end of the screen. Okay, so this looks a lot like some of the slides that we've had already, because I'm repeating definitions so I can do the translation in my head, but from source. So it's like, these are those Lambda definitions. Turns out that it's like, we model the factory functions left and right for either senders using let value, because we're about to compute something that's going to return a sender. So we want to, when we invoke this, we want to take the result of our computation and stick it on the end, not call it directly. It's like, so we're not if we did it with then, we'd get a sender when we, like template nesting, we just want the sender flattened, taking the constructed sender and continue with at that one wherever I've stuck it on the chain. The function that we have is pretty straightforward. It's like we bind the value that we're sticking on the left side into the lambda we're going to have. Since it's left, it's going to be taking two functions, what to do on the left and what to do on the right. I'm using underbar to say that I'm not interested in this, in what I'm using. So compiler, don't tell me I've got an unused parameter. I'm going to send the value on as a just, so we're now chaining a sender, and pass that value into the function that you're giving me eventually. This is the same thing that we did more directly with lambdas. It's like only like that just, it's like we could, it's like write that as a single function, but it's like, this is how you write a function call with senders. The pattern shows up all the time. You could also write that as then L comma X just A. It's like, but then you run into the nesting problem working, inward, outward in terms of things. Right works the same way, only it's concerned with the right side, the right match for the visitor. For figuring out if something is a left, this is just a lambda function. It's like basically just a function object. It's going to construct two functions to pass to our either object. So it takes, and the functions are real simple. It's like we return true for the visiting the first side. We return false if we're visiting on the right side, and we pipe that just like that tuple of left and right functions right into the sender that we're passed in. So not a lot of magic here. A lot of boilerplate though. We do this like similarly for right. We can do the similar code for reading from a left and from a right. It's like we can do the case analysis. Given an either, here's what to do if it's a left, here's what to do if it's a right. Because we're computing a sender, this is a let value, because we want the results of this to be stuck on the end of our chain. And it's like levels of what we're doing. And let's see, like if we look at some test code, let's see, whoops. Yeah. The fact that I'm missing half a line at the bottom of my screen is killing me. So, let's see. This is either. Okay, yeah, here's my test code. Some of these are commented out. I've got a Godbolt link. This is working. This side of it is working with std.exec, isn't working with Beeman execution. There's some other examples that have the opposite problem. Bleeding edge is always fun. But we can use these, and aside from the sync wait noise, this is not code that's really hard to follow. It's like the usage looks very much like what we would expect using any other either type to be with. It's like, so I construct a left, I construct a right. Calling it's like is left on L or R and getting a concrete value out, extra noise. It's not too hard to abstract out that. It's like to get you back down to the value level out of the sender level. But since I'm writing test code, it's like when I have an error, I don't want to hide my errors too deeply in function stacks. This getting things wrong is still a compiler error message nightmare. It's like, in particular, there's a lot of, in all of these frameworks, there's a lot of case statements matching on concepts. I often end up getting error messages out of the instantiation from an entirely wrong branch of the tree that it's doing internally, which means it's like I failed somewhere else, but the error messages are because this is just lost and confused. The compiler isn't telling me about the things that got like pulled out of the overload set entirely already, because I didn't match quite the concept it was looking for. And now I've fallen into a default case, and it says, oh, this doesn't work because as you've constructed an uncopyable tuple. And I'm like, I wasn't trying to do any of that at all. So, it's like, but this all works pretty much the way you'd expect, and we can do that. We can. I won't show you the pair code, but whoops. Come on. So if we look, actually, yeah, it's like might as well, let me switch over to stream because that's the more interesting one. Come on. There's the example, sender stream. Yeah, there's the implementation for stream. Yeah, ignore some of the line noise. It's like for the mathy definition, but it's like after looking at it a bunch, it helped me keep my head straight on when I was doing the translations. And I have here the code that I've got in the Lambda case and how I'm translating that to the sender case. So it's like, if I've got something that acts like a stream and I want the head of it, we're going to take return a just of a lambda that's going to take the visitor for A and A's and just return A and pipe that just into the sender that that I said is modeling the stream. So it's like the stream's then responsible for taking which function is appropriate and giving them the results back. Tail works very much the same. This is very much like pair and list code, where it's like this pattern shows up all the time. Like, give me the first or give me the second, and just return that. So we can, given a stream, I can construct a stream by sticking a value in front of it. So like, because I'm constructing a sender, this needs to be a let value, saying that whatever I compute here, run this function, and what comes out of the function, stick on the end of of my sender chain, or in the graph, wherever I put it. But we just, it's like capture the head and stream. A's are it's like the stream that we're sticking things on. It's a bunch of A's. It's like we're going to return something that wants a stream to operate on. So we construct a just of the value that we want to stick on the front, the stream that we're going to stick it onto, and just pipe that into then stream. So it's like we're just taking these things and calling the functions on them. Test code says this works. It's like acts as expected. It's like the simplest stream that we can come up with for doing this outside of this framework is a const stream. We say a value, and it's like we're not going to keep evaluating it. It's like, but we're going to hold on to our value k, binding it in the lambda. We have a recursive self, and I'm going to pass this lambda to the stream that we're going to stick on the end. So this now becomes the head of what we're doing, that's got the value that's going to be returned from when we ask for the head, and whatever we passed into this function is going to be the tail. Which is always the same in this case because we're just doing this ourselves. It's like more, unfortunately, the example code I hear, it's like I was working with Task and I realized how to do it this morning. But essentially, we need to break the type recursion that we need to. It's like if we're going to construct a task that returns a task that's like itself, we need to have a type that we can interpose so the compiler is happy. I think I can do it with a CRTP, that it's like DeepMar's not sure that it's like this will work, that inheriting from task is sensible. It's like, if it's not, I can do it probably with some other constructor stuff, but it's like, but essentially, we want to return. We want to have a task that returns head and task that is a sender, that is a stream, and you can see how that has the type recursion problem, because it would be a task that returns like an int and a tuple of int and task int comma task int comma task int comma. It's like when you want to have a name in right after that comma, that it's like it's really a tuple of int and stream of int. Like, and once you have that, because it's like this is going to be this is all lazy. It's like you don't have to worry about what's in there until you need to use it. No work's been done yet. So 3 minutes left, a little bit of time for questions. I know this was a lot at 9 a.m. It was a lot for me. Okay, switching back to no, questions starts who, what, when, where. That's right. Proposition, truth value, true or false, not both. Goes up at the end.